So, we are Biomedical Engineering Senior Design Team 10, consisting of Ben Johns, Alex Carlson, Bella Kanasty, and Carter Schluentz, advised by Dr. Hoda Hatoum and Dr. Roger Guillory. We were tasked with designing and constructing a bioreactor where metal alloy stents can be tested for their degradation behavior under physiological conditions. The purpose of this design is to combat the issues associated with restenosis of current generation stents, as 700,000 people are affected by atherosclerosis each year and are required to undergo stenting. Here are some previous research groups' bioreactor designs. We use these designs as a basis to determine how to construct our design. The behavior of stents undergoing flow-induced corrosion is not well documented, and there is a need to be able to characterize the degradation in order to modulate and control it for desirable results. So we created a bioreactor to do that. Here is the completely constructed bioreactor system. The fluid travels from the reservoir to the piston chamber through the aortic root and then into the compliance chamber. There are two different sets of return tubing in this system, one after the compliance chamber and one for the coronary artery. The return tubing completes the loop for our system. Here is a short video of our system running. LabVIEW was used to control the bioreactor and to record data. Here is the front panel of the code. A borescope was used to record live footage of the stent. Here is a video and an image from the borescope. We performed static immersion testing on the bioreabsorbable stent wire segments that are intended for future use in degradable stents. This testing was designed to provide baseline corrosion data and to help the team understand how long the dynamic system needs to run to begin to see corrosion activity. 6-well plates with 2 milliliters of DMEM in each well were used to perform the static immersion testing. 1 wire was placed in each well and removed after 24 hours, for up to 5 days until no wires remained. DMEM was collected and preserved for future pH analysis. There was a control plate containing DMEM only for pH comparison. This shows the results of day 1 and day 5 wires after being imaged in the SEM. There's a strong corrosion pattern observed after 5 days, and the backscattered image, as well as the elemental mapping, corroborates this. The system leaking was our biggest challenge. We worked to solve this by redesigning the piston and chamber to reduce leaking to a minimum. This semester we completed the system construction, the incorporation of LabVIEW, and preliminary system testing and corrosion analysis. The future work for our system includes deploying stents into the arteries and collecting and analyzing dynamic data. We also recommend building a more professional and permanent frame. The piston pump mechanism should be redesigned using commercial products to minimize some of the challenges associated with the pump. Lastly, it would be ideal to miniaturize our system for better portability and to fit in a biosafety cabinet. These are the standards used for the design and construction of our system. ISO standard 5840 is a collection of standards used for cardiovascular prosthetics. We would like to acknowledge our sponsors and advisors, Dr. Guillory and Dr. Hatoum, as well as Michigan Tech students Nick Butcher and Mark Austigan, who helped with the wire processing. We would also like to acknowledge Steve Lehman, Dr. Dan Seguin, and Elizabeth Miller for their assistance on various aspects of the project.